Welcome to this explainer. Okay, we're going to jump right into a fascinating mathematical paradox that sits right at the very heart of model selection in machine learning. Seriously, have you ever wondered why our seemingly best models, the ones that absolutely crush it during training and validation, are constantly lying to us when we actually deploy them? Well, today, we are unpacking exactly that. So the crucial point we have to tackle is our core antagonist here, optimistic bias. When we build models, we naturally want the highest accuracy or the lowest error, right? But the very act of picking the best algorithm almost mathematically guarantees that we are going to overestimate its true performance. In this explainer, we're going to use rigorous mathematics to uncover exactly why this happens, drawing directly from some really advanced computer science lectures on nested resampling. Now, to ground all the complex math we're about to see in a relatable reality, let's use a great analogy straight from the source material. Imagine a professor grading an exam. If you let a student try that exam several times, and only the absolute highest grade ends up on their transcript, what happens? Well, naturally, that highest grade is going to slightly overestimate the true average academic performance of that student. Selecting the maximum inherently inflates perceived ability. And guess what? Algorithms do the exact same thing. All right, so here is our roadmap for this explainer. We're going to cover the math of optimistic bias, defining the selector algorithm, the order of expected values, meta-selectors and holdouts, nested cross-validation loops, and finally, we'll wrap up by decoding a real exam question. Okay, let's jump right into section 1, the math of optimistic bias. This formula perfectly illustrates the exact mathematical foundation of our problem. It applies Jensen's inequality to the maximum function, which is inherently convex. Look at the equation. We have the expected value of the maximum over a set of estimators, denoted as theta hat belonging to the set big theta hat, evaluated on a random variable sample S. The inequality proves this expectation is always greater than or equal to the maximum of the expected values of those individual estimators. In plain English, taking the maximum value out of a set of options evaluated on the exact same sample guarantees you will overestimate the goodness of that candidate. And that holds true even if every single estimator was completely unbiased to begin with. Let's boil this down to the absolute smallest possible case. Just two options. First, consider the true maximum, theta max. This is the actual, absolute best true performance between two hypotheses, theta 1 and theta 2. Now, compare that to the estimated maximum, theta hat max of S. This is the maximum of the estimates calculated from a specific data sample S. Because of Jensen's inequality we just talked about, the expected value of what we calculate from our sample data will consistently be larger than the actual true maximum. It creates this perfect illusion of a perfect choice. Moving on to section 2, defining the selector algorithm. So we define this selector algorithm, denoted as H-cell. Given a sample of data, lowercase s, this algorithm looks at two hypotheses, H1 and H2, and simply selects the one that performs best on that sample. Mathematically, it's the argmax of theta hat 1 of S and theta hat 2 of S. Now, to measure how well this selector algorithm will actually do out there in the real world, we define its expected prediction performance, theta cell. This is the expected holdout utility, denoted by the function g of the selector algorithm when trained on a sample S and evaluated on entirely new, independent, and identically distributed data z new. Right, section 3, order of expected values. This hierarchy right here meticulously orders our expectations, and it's super revealing. If our two hypotheses have different true performances, meaning theta 1 does not equal theta 2, the true performance of our selector algorithm, theta_cell, sits strictly between the worst hypothesis, theta min, and the best hypothesis, theta max. Why is that? Well, because sample randomness means the selector won't always pick the best option. Sometimes it just gets fooled by the sample and picks the worst one. But crucially, look at the very end of that chain. All of these are strictly less than the expected value of our sample estimate, E of theta hat max of S. Even in the case where the two hypotheses are exactly equal in true performance, Jensen's inequality dictates that our expected maximum estimate on the sample is still higher than the true performance. The math proves our selector algorithm inherently falls short of the true maximum, while simultaneously creating the illusion that it's doing way better than it actually is. Which brings us to section 4, meta-selectors and holdouts. To try and get a more honest evaluation, we typically use a holdout estimator. Instead of evaluating on the whole sample, we split our data S into two parts, S-train and S-test. The holdout estimator for an algorithm A, denoted theta hat A, t of S, evaluates the hypothesis H, which, remember, was trained strictly on S-train, using only the fresh S-test data. This is a fundamental remedy to reduce bias, giving us a much more honest look at the algorithm's expected holdout utility. But here is where we level up to what the source material calls the Meta-Selector algorithm. This algorithm doesn't just use holdout data to evaluate. It uses it to actively choose the winner between two entirely different learning algorithms, like, say, a random forest versus a neural network. Step 1, you train both algorithms on the training split to generate hypotheses H1 and H2. Step 2, you test both of those hypotheses on the test split. Step 3, return the hypothesis that performed better on that test set. Seems perfectly reasonable, right? Well, the crucial point is we must formalize the true expected performance of this new Meta-Selector. We denote this as theta underscore Meta-Cell. This equals the expected utility, function g, of the Meta-Selector trained on sample S, but evaluated on entirely new, unseen, independent, and identically distributed data, z underscore new. We are essentially treating the entire selection process itself as one giant, nested learning algorithm. And this leads us to the climax of our mathematical story. Even when we use holdout estimators to try and be completely honest, if we use them to make a selection, Jensen's inequality strikes again. Just look at the inequality chain. The true expected performance of our Meta-Selector theta underscore Meta-Cell is still trapped below the true maximum theta max, and crucially, it is strictly less than the expected value of the maximum of our holdout estimates for algorithm 1 and algorithm 2, evaluated on sample S. The optimistic bias persists. The very act of selecting the best from the test set essentially turns that test set into part of the treating process, inherently overestimating the result. Section 5. Nested cross-validation loops. So, how do we practically deal with this? If you have enough data, you separate it into 3 distinct chunks. Training, validation, which is strictly used for the Meta-Selector to choose the algorithm, and a completely locked-away test set for the final honest evaluation. If you have too little data, you use repeated holdout or cross-validation for those first 2 parts. And if you still have too little data, you add an outer cross-validation loop that uses an inner cross-validation loop recursively. The inner loop acts as our Meta-Selector. It explores the hyperparameter or algorithm space to find the winner. But the outer loop is strictly reserved to honestly estimate the prediction performance of that entire meta-selection process. Finally, Section 6, Decoding the exam question. Let's apply literally everything we just learned to a real-world scenario. Here is the exact wording of an exam question from the source material. We have 2 learning algorithms evaluated on holdout data. We define the statistic theta hat max as the maximum of their holdout accuracies, theta hat 1 and theta hat 2. The question asks, is this theta hat max an unbiased estimator of the true maximum if the algorithms have equal expected accuracies? What if their true accuracies are different? Let's analyze the traps hidden in the answer options. Option A tries to lure you in by claiming it's unbiased if the true performances are perfectly equal. Option B claims it's unbiased if the performances are different. The trick here is totally honing in on that specific word, unbiased. Remember all the math we just exhaustively went through? And here is the resolution straight from the professor's lecture. Neither A nor B is correct. The true answer is that neither statement is true. We have proven mathematically, through Jensen's inequality and the formulas for expected values, that taking the maximum is inherently flawed. Both are biased because they are optimistic. By choosing the better out of the 2 on a specific sample, you mathematically guarantee an overestimation of the true performance. To wrap things up, whenever you select the best out of several options, whether we're talking about hyperparameters, feature sets, or entire algorithms, the performance metric you observe during that selection process is always an optimistic illusion. Optimization, in a weird way, ruins the very metric it relies on. So the next time you see a flashy claim about a state-of-the-art, best-performing model, you really have to ask yourself, how many models did they test to find that one? And did they use an entirely separate nested loop to give you that final accuracy number? Because if they didn't, the math tells us for sure they are likely suffering from the winner's curse.